everyone, I'm Lujia. Here I'm going to tell you about our work, the ParaX. The big data era brings several challenges for data analytics as information becomes available in such volume, velocity, and variety that it cannot be processed by traditional algorithms and systems. In recent years, deep learning has been emerging as an effective approach for many fields of big data analytics, such as image recognition, natural language processing, and recommendation. DL platforms such as TensorFlow, PyTorch, Caffe, and MaxNet support both CPUs and GPUs for training and inference of DNN models. Although CPUs are less efficient than GPUs for deep learning, they are now widely used in both training and inference in the cloud environment. This is not only because CPUs can provide low latency with small batch size for online inference, but also because there are large numbers of CPUs which would otherwise sit idle during off-peak periods. For instance, FB Learner is a hybrid system of Facebook, which mainly uses GPUs in training and online inference for high throughput, and adopts CPUs in online inference for low latency. Since the diagonal loud circles leaves a significant number of CPUs available, FB Learner also heavily uses CPUs in its offline training and inference tasks. However, it is still challenging to fully exploit the power of manifold CPUs on the mainstream DL platforms, which are originally designed for and currently focused on GPU-based deep learning computation. The figure depicts the result for bandwidth of CPU, where it is the memory bandwidth that bounds the execution of the activations and batch normalizations layers and causes CPU starvation. About half of the bandwidth is idle at the convolution layers, which results in a low utilization of the precious CPU memory bandwidth. The root cause of the low utilization of the precious memory bandwidth is that the current DL platforms only one single instance is assigned to one CPU, where an instance is a batch of input data jointly processed in an iteration. The per-layer barriers enforce synchronous executions of the operations, making the limited memory bandwidth of many core CPUs become a bottleneck and causing intermittent CPU starvation at the access-intensive layer. To understand the impact of bandwidth contention, we evaluate the ratio of execution times of the compute-intensive layers to that of the access-intensive layers running MaxNet on one NUMA Intel A280 CPU, respectively for inference of ResNet-50, LSTM, and NCF models. As shown in the upper figures, the execution times of the compute-intensive layers are smaller than 1.5 times, comparable to that of the access-intensive layers. In contrast, when conducting the same experiment on a P100 GPU, the execution times of the compute-intensive layers are up to 2.7 times that of the access-intensive layers. We further analyze the scalability of the compute-intensive operations and access-intensive operations by executing them layer by layer using a one NUMA 8280 CPU to infer ResNet-50 on MaxNet. The results show that the speedups of the three operations are similar before the number of the threads increases up to 7. Afterwards, the speedups of BN and activation increase very little, while that of convolution is still almost linear with N. This is because the bandwidth utilization of BN and activation almost reaches the maximum bandwidth capacity when N is larger than 7, while that of convolution reaches only about one half of the maximum capacity even when the number of the cores is as high as 28. To alleviate the problem of memory bandwidth contention, our basic idea is to overlap the executions of various layers on different cores, so that the compute-intensive layers could lend the surplus bandwidth to the access-intensive ones. ParaX proposes to divide the input data of an iteration into batches, and assign each CPU core with one instance, which we refer to as one instance per core, as shown in the figure below. This allows each core to individually process its instance without barriers, making it possible for the access-intensive layers to make use of the surplus bandwidth of the simultaneous compute-intensive layers. One instance per core provides an opportunity for bandwidth landing between the memory cores of a CPU, each of which runs one thread processing one instance. There is certain randomness for the execution times of the same operations on the same-sized batches, especially when the number of the threads is relatively large and the network is deep enough. Therefore, ParaX adopts an arbitrary overlap scaling policy, which relies on the randomness of the operation's execution times to overlap the execution of access and compute-intensive layers on different cores. ParaX follows synchronous SGD to update the parameters by using the gradients from the instances for every training iteration. The downside of one instance per core for parameter update is that it potentially increases the synchronization overhead as the number of instances increases, which might even completely counteract the benefit of layer overlapping. Existing synchronization mechanisms of currently DL platforms such as parameter server are initially targeted for distributed scenarios and thus not suitable for synchronization of the many instances of a CPU. To improve the synchronization efficiency, ParaX designs a NUMA-aware gradient server mechanism which leverages shared memory to allow worker instances to directly access the weight. As shown in the figure, one CPU runs one gradient server, which doesn't process its own weight but shares the weight with the instances. In order to eliminate the costly per iteration memory copy, on each NUMA there is a complete copy of the weight in the local memory, so as to avoid frequently remote memory access within an iteration. We have implemented ParaX on MagNet. We evaluate the throughput of ParaX in training and inference, ResNet50, MobileNet, LSTM. The figure shows the speedups of ParaX to MagNet, where for training and inference the speedups are respectively 1.7 times to 2.9 times and 2 times to 2.1 times. We further measure the effectiveness of overlapping scheduling, that is, the CPU utilization during the inference of ResNet15 on ParaX. The figure shows the CPU utilization of a period of 50 seconds, where the utilization keeps always high. The mean utilization of the entire training procedure achieves as high as 94.8%. We also measure the mean memory bandwidth utilization during the inference, which is about 88.6%, much higher than that of the original MagNet. Compared to the original one instance per CPU paradigm adopted by current DL platforms, ParaX significantly improves the CPU and memory bandwidth utilizations. Thank you.